here's a picture, if it'll come up, sorry, of an atom. This atom is helium. Good. Okay, there's one. This atom is helium. You see there's 2 neutrons, 2 protons, and 2 electrons in this atom. When we move on to the atomic configuration, again, what an atom wants to do is to have those 2 things happening. Have its outer shells filled with electrons and to have electrochemical neutrality. So when you look at the periodic table of elements, there are some atoms that do this, but most don't. Some either have electrochemical neutrality or their shells will be full, but not both. So when both conditions are not met, we're moving up now from atoms to molecules, which will be the building blocks of minerals. And we are wanting to, with atoms, group them together by bonding. And there are several different types of bonds. The bonds that we're interested in this class are 3, ionic, covalent, and hydrogen bonding we'll look at when we look at water molecules. There are many other types of bonds. Van der Waals bond, there are hybridized bonds, there are metallic bonds. So here is an example of ionic bonding. In this case, we have a sodium atom. And how many electrons are in its outer shell? 1, yeah. So what this atom wants to do to anthropomorphize an atom is to get rid of that 1 electron. Then you have chlorine, and how many electrons in its outer shell? 7, right? And you need 8 in that shell. So what will happen is sodium will give that electron to chlorine, and now they're both happy from the outer shell's full point of view, but they're not happy because now they both have an electrochemical charge. Sodium lost a negative, and so it's positive. Chlorine gained a negative, so it's negative. So now the way they get around this is to stick together, like similar to if you comb your hair really fast, you have static electricity. With a static charge, these 2 atoms stick together. This is a weak kind of bond, and we care about this from a disaster's point of view because when you have a weak bond, then you're going to make a weak mineral and therefore a weak rock, and so you'll end up having maybe more landslides, or an earthquake will be greater. An example of an ionic bond is those of you who are writing with pencil. You're using a weakly metamorphic mineral called, what's in your pencil? Not lead, it's graphite. Yeah, graphite. Graphite is pure carbon. It's ionically bonded. And what you're doing when you're writing is you're breaking these weak bonds and leaving some carbon behind on your paper. So this is a pretty weak type of bond. You'll see this in sodium chlorine. We'll look at the mineral that's composed of sodium chlorine, which is called halite. Next, we have covalent bonding. And in this type of bond, you're not giving an electron to a neighboring atom. You are sharing electrons. This is a very, very strong type of bond. So what's going on here is you have fluorine, and fluorine, 2 fluorines, they both have 7 electrons in their outermost shells. And so what happens is a real sort of gross simplification, but electrons spend 50% of their time in one shell, 50% in another shell, and you essentially fool the atoms into thinking that their shells are full and they have electrochemical neutrality, which again are the 2 things we want to do. This type of bond is very strong. And to demonstrate how strong it is relative to ionic bond, does anyone know what happens when you take the carbon from your pencil lead, from graphite, and instead of bonding it ionically, you bond it covalently? Yeah, it's a diamond, the hardest substance known to humans. It's the same exact chemical formula as the graphite in your pencil. However, it is the strongest substance that we know of. So those are the 2 types of bonds we care about from an atom point of view when we're making minerals. But again, we will look at hydrogen bonding. We'll look at other types of bonding in the class later. We care about those 2 types because they create minerals. So we're going from atom to molecule. Now we're at mineral. And the thing about minerals is very difficult to define. If you take a class called mineralogy, there's a 7-page definition of what a mineral is. So it's quite complicated. But for the purposes of our class, we can distill it down to about 6 simple definitions and get 90% of the way there. And I'll tell you how some of these definitions would break down. So you need a full definition. But bonding creates minerals. Here is the mineral, for example, that you get when you bond that sodium and chlorine together ionically. You get table salt, sea salt, you get salt. The mineral is called halite. And this is what it looks like. Note the chemical structure. There's a regular, orderly pattern to it. So this chemical structure is important, which we'll get to. But there's halite, ionically bonded sodium and chlorine. So this definition of a mineral, there's 6 parts. They're all very simple. And we're getting to a mineral because, to sort of skip ahead for a minute, when you define a rock is a very simple thing to define. It's an accumulation of 1 or more minerals. That's it. So these are the building blocks of rocks. And what a mineral has to be is, number 1, solid. So for example, if you are outside coming to class and you chipped a little piece of ice off of a puddle that was out there, that would fit this whole abbreviated definition as well as the expanded definition of a mineral. Ice is a mineral. But what would happen to the ice if you passed it around as a kind of show and tell about what a mineral is? It melts, right? And so therefore it's no longer a mineral. Excellent. So ice is a mineral, water is not. We'll see this when we talk about igneous rocks. Igneous rocks are made of lava or magma, right? And the lava and magma are liquid, therefore they're not rocks, but the second they cool, they become rocks. So a mineral has to be solid. It also has to be naturally occurring. So going back to the definition of, or the covalently bonded carbon, diamond, right? Hardest substance known to humanity. We talked in Geoscience 1 about how they're really a kind of false economy. There's nothing spectacular about diamonds. We geologists think of them as drill bits. They're easy to make in the lab. You just have to put carbon together, not a rare element, under high pressures and temperature. And it's so easy to do that we do this in many different applications. For example, when we were sending fighter jets over to the Middle East a long time ago, the windscreen, the radar housing would be sandblasted by the large amount of sand that's in this arid environment. And so the windscreens would get sandblasted so you couldn't see. Not good for the navigational capacities of the jet. So what we did was to bring the windscreens and the radar coverings into the lab and grow a few microns thick of diamond, covalently bonded carbon, to the outside of the windscreen. So it's clear, but it's also, we'll look at Mohs hardness scale, a lot harder than the sand that's bouncing off the glass, and so it does nothing to the glass. But I'm kind of telling an untruth by saying we're growing diamond because in order for something to be classified as a mineral, it has to be naturally occurring. So we can make diamonds, in quotation marks, that gemologists can't even tell the difference between the ones that we fabricate and the ones that are naturally occurring. However, from a strict geology point of view, the ones that we create, though indistinguishable, are not true diamonds because they're not minerals. Next part of the definition is it has to be homogeneous. Homo means the same, genus, made of, so it's the same throughout. Now we'll see how there will be slight variations in the chemistry of a mineral, but by and large it has to be the same everywhere you go in the microscopic scale within that sample. It's the same. There are no variations in the mineral. It also has to be inorganic. Here's also where the definition breaks down a little bit. So it has to have come from non-living. Simple, right? So the definition breaks down, and you have to have this expanded definition when you're talking about coal or when you're talking about certain types of limestone. Because coal, as we'll see maybe a little bit in this class, coal comes from tropical swamp stuff. So it came from organic materials. Coal is classified as a sedimentary rock. A sedimentary rock, and any rock, is defined as being made of minerals. So now we're trapped because we can't then call coal a rock because it has to be made of minerals and it's made of something that is organic. And it's the same thing with limestone, calcium carbonate, that's made as a result of coral reefs that get destroyed or eroded a little bit, and then the material gets reworked and turned into a sedimentary rock called limestone. It came from the living, hard parts of living organisms. So that's why some of these definitions break down, but it has to be, or inorganic, parentheses, except for when it's not. And I wouldn't ask you about the exceptions, because you just need to know the main points of this. So it also has to have a specific chemical composition. We talked about graphite, C. We talked about diamond, C. Some of the minerals are a little longer, NaCl, halite. Some can get to be very long. When you're talking about clays, you have hydrous aluminosilicates. There are 8 or 9 different elements in different fractions that are in the mineral. But the bottom line is you have to be able to write a chemical formula down to describe that mineral. So it has a specific chemical composition. And it also, that's what this picture is here, has a specific structural arrangement. And what this means is that it has to be a crystal. There has to be a regularly spaced pattern to it. So the specific structural arrangement means that it's a crystal. And crystal, quartz, is a very common mineral that's present in a lot of rocks. As we'll see, the surface of Earth is really just kind of a glass shell. So it's silica. And it's indistinguishable from the glass in the window panes, except silica, in a mineral form, if you looked at it, has a regularly spaced pattern. It has a specific structural arrangement. If you could look in a microscope at the glass in this room, it would be randomly bonded. It was cooled quickly and randomly bonded. There's no order to it. You could say that there's such thing as crystal glass, right? Your mother's good stemware, your family's good stemware. That's crystal. That is bonded in a regular pattern. However, then we get to the point that it's not naturally occurring, so it's also not a mineral, but it is crystal. It has a specific structural arrangement. So that's the definition of a mineral. But again, if you take a class called mineralogy, which is a study of all these amazing minerals, it doesn't get you very close to identifying a mineral. So if you have a mystery mineral and you want to identify it, you have to go through a set of diagnostic tests, which are pretty simple as well. And so in mineralogy, you go to your lab and you get a box of minerals, and you have 3 hours, and you have to classify them all. You have to identify what is this mineral. And so mineralogists who do this, students and researchers alike, would look at this mystery mineral, and the first thing they would do is to figure out the hardness. And hardness is given in terms of Mohs hardness scale. Mohs hardness scale is a relative scale that goes from 1 to 10. There are no units on it because it's just relative to each other. And 1 through 10 are different index minerals that go from the softest, talc is the softest mineral there is, all the way up to diamond on the other end. So talc and then gypsum, calcite, going up through the harder minerals. So you have this mystery mineral. What you do is to scratch it against the index minerals. And if your mineral scratches the index mineral, you know that your mineral is harder. If the index mineral scratches your mineral, then you know that your mineral is softer. So if we did this to this mystery mineral, this would have a hardness of about 2.5. You can also use things like steel nails. You can use pennies. You can use your fingernails. We know the hardness of certain common things. So hardness scale. How hard is the mineral? The next diagnostic tool you might use is to figure out the streak. And I'll show you a picture of that next, the next slide. Streak is defined as the color of the mineral in its powdered form. And we like to see the powdered form because that's the unoxidized, unweathered form of it. The way that you do this is simply to take an unglazed bathroom tile and streak your mineral across it. And oftentimes you get exactly what you'd expect. With this mystery mineral, if you have an unglazed bathroom tile and you streak it across or streak the mineral across it, you'd get a clear, whitish kind of streak. But sometimes you get really neat stuff. You can take a silvery gray mineral and it will streak clear. You can take a gold mineral and it will streak black. You can take a silvery mineral, it will streak bright red. I'll show you that. Those are dead giveaways. If you have a silvery mineral and you streak it and it's bright red, you know, game over, it's hematite. That's all it can be. So some of these things are easier to identify than others, but the streak is the color of the mineral in its its powdered form, unoxidized form. Next is the crystal form. And so there are cubic arrangement. This is called orthorhombic. It's a little offset. And if you picture a brick wall, so the first layer of bricks and the next layer of bricks is offset a little, like the halite that we looked at in cartoon diagram a couple slides ago, and then offset a little. What will happen in macro scale is it will reflect the crystal form. And so this is a little offset. It's called orthorhombic. But you can have cubic, you can have prismatic, you can have all different types of crystal form. Next, we look at cleavage. And cleavage is defined as the way that the mineral breaks along weak planes. So the way the mineral breaks along weak planes. Sometimes there's no cleavage. I'll show you some pictures of cleavage. It takes a little bit of experience to figure out cleavage sometimes. We all, I think, know this mineral called mica. Maybe you think it's a rock, but it's a mineral that cleaves or breaks in one direction. So it's really easy to flake layers off of the mica in one direction, but if you tried to break a whole sample, you wouldn't have much luck. It's a silicate mineral. It's pretty hard. So that cleaves or breaks in one direction. I'll show you some that cleave or break in two directions. This one cleaves in three directions, and this gives you the nice cubic look to these. You see, if you're picturing holding this, it will break parallel to the screen. It will break going into the screen, and it will break in this direction. So the X, Y, and Z directions, it will break easily in three directions. So that's three directions of cleavage. You can have 4, 5, 6. Some of them are really difficult to tell because there's 6 different cleavage directions. Color is typically a poor diagnostic indicator of minerals, but sometimes you can use it. And the reality is you use these different indicators differently for different samples and sort of get the hang of it, sort of figure out shortcuts for different things. But color, in this case, this is clear. And color, again, is a poor diagnostic indicator. I'll show you something called polymorphism, which is different, multiple shapes or multiple iterations. So there's this mineral, hematite, that has 3 different colors it can be. Quartz, for example, that can be 7 different colors because it's clear, and if there's tiny amounts of impurities, whether it's copper, whether it's manganese, magnesium, it will color it many different colors. If you go to a gem shop, you see a lot of crystals that are quartz, and they have different pretty colors because of small amounts of impurities. Luster is defined as the surface sheen, and luster can be metallic, non-metallic, can be opalescent, so they're different different lusters it can be. But the 2 most common lusters are metallic and non-metallic. So then fracture, I'll show you also a picture of fracture soon. Fracture is defined as the way that the mineral breaks in the absence of weak planes. So the way it breaks in the absence of cleavage. So if you take quartz that has 4 nice directions of cleavage and gives it a prismatic look, and you shatter it with a hammer, what will happen is you'll see conchoidal fractures. I'll show you a picture of this, like bowl-shaped depressions. So you smash it, and sometimes fracture can give you an idea of what the mineral looks like and what the mineral is. These last 2 you don't tend to use too often. There are a couple of cases where you would pass a sound current or electric current through, and the rate at which these things travel will tell you something about the mineral. When we get to volcanoes and igneous rocks, we'll look at this mineral, really neat mineral. It's a common mineral that, that has something called solid solution. So it's crystallizing out of a melt. It's crystallizing out of magma. And when it first starts to crystallize, it will use sodium. And as the temperature cools in the magma, and as more and more of this mineral is made, the using of sodium depletes the remaining liquid of sodium, and so it will start to use calcium. So this mineral will have 100% sodium, and then as it cools, it will start to use 1% calcium, and then 2%, and then 10%, all the way up to, at the very end, before the magma is all the way cool, it will be using 100% calcium. But sodium feldspar and calcium feldspar, it's called orthoclase, are two different minerals. So where do you cut them off? And they look the same. And all of these diagnostic indicators come back the same. So there are examples where you need to figure out how much sodium, how much calcium is in there. And so you would use these special things. So a couple of pictures of what we just saw. This is crystal form. This is actually a piece of schist, which is a metamorphic rock. So one of the last things we'll see today. And this schist has little crystals, or larger crystals, of a mineral called corundum, which you know as, anyone know what this looks like? It's garnet. So the gem garnet is actually corundum. And this has a crystal form that's prismatic. It cleaves in 5 directions. And it's also, when we talk about economic mineralogy, we take this, it's very hard, and we grind it up and we use it as sandpaper. So when you have sandpaper, you have the same exact mineral as a garnet on your hand. So there's crystal form. Here's quartz that has been shattered with a hammer, and you have something called conchoidal fracture. Conchoidal fracture is this bowl-shaped depression where this would otherwise be a neat prism. And this is polymorphism, again, this thing that I told you about. There are 3 different types of the same mineral. And this mineral is called hematite. It's an iron oxide. We mine this. We use it for many different applications, iron, industrial applications. But what you're seeing here is that there are 3 very different colors. There's a red, earthy, or iterations. Red, earthy, then you have a red metallic, and then you have this silvery gray metallic. And this is a streak plate. This is the unglazed bathroom tile. And regardless of which of these you streak on the unglazed bathroom tile, you get a bright red streak. So again, that would make sense for the mineral on your left, but for the mineral in the center to get a red streak out of a silvery gray mineral, you know exactly what it is. So there's a picture of calcite. This is the mineral calcite that will make limestone. We'll look at when we talk about sedimentary rocks. Very common mineral, calcium and carbonate stuck together. And it's on a piece of basalt, which is an igneous rock. Then we have Muscovite Micah. We talked about mica, right? So you all know mica. There are 2 kinds of mica. There's Muscovite, which is a lighter silvery color, and then biotite, which is dark black. That purple diagram right there is to show that there's one direction of cleavage. So you can flake these layers off, but to try to break the whole sample, you would not be able to do that. So it has these different bonds depending on the direction that you're looking. Here is, again, looking at cleavage. This is 2 directions of cleavage. And this is Orthoclase Feldspar, very common mineral. You might recognize it as the little pink chunks in granite. So common igneous mineral. And this cleaves along the top face. See, there are 4 samples here. It cleaves along the top face, and it cleaves going into the board. These aren't cut with a rock saw. This is how it grew. But if you look at the front face, in a way that the mystery mineral had a nice cleavage plane along the front, this is blocky and irregular. So this just has 2 directions of cleavage. So the previous one, it's really easy to see 1. It's easy to see 2, it's easy to see 3. Beyond that, it starts to get kind of complicated. So what is our mystery mineral? Once we've run it through the diagnostic test, there's 2 things that it could be. Everything else is the same with these 2 minerals. That top one is halite, the bottom one is calcite. All of those other diagnostic tools will come back the same, except for the crystal form here. Halite is set up so that it is in a cube, and calcite is a little bit offset. So these are different minerals, and you can tell by the crystal form. Sometimes you can cheat in the lab. Halite obviously will taste like salt, so you see sometimes lazy students that will taste it just to see what it is. Not good, because a lot of minerals contain lead, but that is halite versus calcite. And then I show you this last one because this is a mineral hornblende that has 6 directions of cleavage. Really difficult. I just abandon that and look at other things at that point. When we start talking about igneous minerals that make igneous rocks, there are 3 or 4 that are all this. They look like this, hornblende, pyroxene, amphibole. They look like this. They're dark, they're silicates, they're hard, and they have lots of directions of cleavage. So we'll look further at those when we look at igneous rocks. So that's a little bit about minerals. And the reason that we are looking at minerals, again, is because we want to look at rocks. We want to look at the material properties of rocks, the origin of rocks, and specifically how these rocks will hold up in the face of natural disasters. What sorts of rocks we should be building on, what sorts of rocks we should maybe avoid. So minerals make rocks. You all know there's 3 types of rocks, igneous, sedimentary, and metamorphic. And this is a picture of a igneous rock called diorite. So minerals make up rocks. Rocks are an amalgamation of 1 or more minerals. So now that we're at the top, we've made rocks. Let's think about destroying them. Destroying them is the first step in making a sedimentary rock. We've gotten up to the top. What sorts of things are destroying this mountain? You see these rocks are not in great shape. Yeah, excellent. Rain. Water is a very powerful weatherer of rocks, both in a physical sense. It can go in and smash rocks that are weakly held together, but then also in a chemical sense. It can dissolve things, as we'll see. So rain, what else? Yeah. Good, excellent. Wind. So wind itself, unless it's a really high wind, it won't destroy them, but it will have sand in it, which will sandblast the rocks. Can you think of anything else that's going on here? Yeah? Excellent, yeah. Plants are a very, very powerful weather of rock, both in, again, same with water. They're physical and they're chemical weatherers. So the roots will go in and break the rocks apart, but then also the roots secrete organic acids, and so the acid will wear away the rock. So excellent, yeah. Ice? See ice doing this? Ice is also a very powerful weatherer because we'll talk about water in this class. And with regards to water, water will expand when it freezes. Those of you from last semester remember this. It's not the case with other substances. But water, when it gets into a crack, it will freeze, it will expand, and it will jack apart the rock. And then more water will get in, and then that will freeze, and it will jack apart the rock. So there are many processes on Earth that are going to make for disasters, but that will, I'll put the rest of them out, that will destroy rocks. And destroying rocks is the process of weathering. So we have wind blowing on this, ice forming and cracking the rocks apart, water. Heat can actually just break apart rocks just by heating and cooling, because you know that heat is manifested as vibrations in the atomic structures of the rock, right? So if you have a rock exposed to high temperatures, the desert, for example, is really good at having these temperature extremes because there's very little water there. So in the daytime, the sun is beating down on these rocks, and the molecules of the rocks are vibrating like crazy, and the rock mass expands. Yeah?
Would all rocks expand at the same temperature?
Good question, and no. Yeah, that's a good question. No. It has to do with the material properties of rocks, what's there. Yeah, good question. But they all will expand to some extent, and then when it cools in the desert at night, then they shrink. You can think of it sort of like stone lungs. You can imagine this isn't good for the integrity of the rock to be expanding and contracting, expanding and contracting. Micro cracks will start to form, and you'll break up the rocks. But yeah, good question. And then we already talked about root growth. And then animals and humans. Animals burrowing, digging, worms, tunneling. We humans, as we'll see when we talk about landslides, are fantastic breaker-uppers of rock, right? Every time you want to build a road, you have these rock cuts. Every time you want to build a building, you excavate down into the subsurface. So you're destroying the rocks in many ways. Humans are. The process of destroying rocks is called weathering. And there are 2 types of weathering. One is mechanical weathering. So that's kind of a duplicate slide almost. Mechanical weathering means you do not change the chemical structure of the rock, what you're doing is breaking one rock into two rocks into four, and things like wind and ice would do this. You see this as a pile of shale or slate, you can't tell from looking at it, and it's peeling off in these onion-like layers as a result of gravity, as a result of wind, etc. So that's mechanical weathering. You're breaking a rock into smaller pieces without changing the chemical formula, the mineralogy of the rock. What's going on with this? And then you can change the mineralogy by weathering in a chemical fashion. Chemical weathering happens as a result of oxygen, oxidizing rocks. Water is the most powerful chemical weatherer, as we'll see when we talk about weather, violent weather. Water is polar, which means one side is positive, one side is negative. So water, when it falls as rain, can attach to a rock with its positive side and rip off an ion that would be negative were it in solution. And with equal ease, it can attach with this negative side and rip off an ion that would be positive were it in solution. So water is very good at chemically weathering away rocks. And we'll look at this when we look at something called Bowen's reaction series and the fact that minerals don't weather away chemically at the same rate. I think this is fascinating. To go to the beach. Go to the beach in Boston. What is on the beach? Sand. And what's sand made of? Yeah, it's made of quartz. So it's silica. Grains of silica, grains of quartz. What is the source area for beach sand around here? Where's it coming from? What was weathered away to make this beach sand? Think about up in New Hampshire. It's a good example of where the source material is. What's New Hampshire known as? The what state? The granite state, right? There's 7 different minerals in granite, and it's being broken up and weathered and brought by rivers to our beaches. So then why aren't there 7 different minerals in the beach? All you have is perfectly round grains of quartz, maybe a little bit of mica. The answer to that is that, as we'll see when we talk about making minerals later, when we talk about volcanoes, crystals or minerals form at different temperatures, and the ones that are the most stable at high pressures and temperatures are the least stable at the surface. So when water falls on the granite state, the rain preferentially eats away the minerals that are the least stable at low pressures and temperatures, and water does not eat away silica. So by the time that stuff gets chemically and physically weathered and brought to our beaches, all that's left is quartz. The other 6 minerals, or 5, because sometimes there's some mica, are all gone. So chemical and physical weathering or mechanical weathering makes sedimentary rocks. Here's a picture of sedimentary rocks. We go into sedimentary rocks a lot in other classes, but for the purposes of this class, know that if you had to make a generalization, sedimentary rocks aren't really great to build on. They are not really great in withstanding things like earthquakes and mass wasting. They're weakly held together because of this process. This is a summary slide, so I have a slide on each one of these bullets, so I'll go rapidly through it. This one, and then we'll slow down for the next one. The process of making sedimentary rocks, we've already weathered away the rocks, and then we'll look at transportation, deposition, compaction, cementation. So we weathered, right? Chemically, mechanically weathered away rocks. So you have little pieces, if you're talking about mechanical, but then you have solutes. You have dissolved particles in water as a product of chemical weathering. The next thing you do is transport those things from the source area to ultimately the next step is deposition. Towards the depositional area where they lay down their final resting place. So the transportation is the moving part. And again, water plays a really important role here. Wind can blow things, ice can carry things. Water is a tremendously effective mode of transport. And here you see transportation coming into Death Valley, California. The sediments are the product of weathering of that mountain. So transportation is exactly, you have an intuitive feel for transportation, right? Moving the sediment and weathering plus transportation. This isn't a separate step. Weathering plus transportation is called erosion. So if you've heard of erosion, it's a combined term that describes the breaking up and moving away of rocks from their source area. this is going to be very different from landslides, as we'll see. What's this a picture of? Cape Cod, right, exactly. Cape Cod didn't used to be there before the last glacial maximum. Cape Cod is the erosion of the granite state of Maine, a part of Massachusetts. So what happened was these glaciers came down from the north and they scraped up the rocks and carried them to their terminal position, which is Martha's Vineyard in Nantucket. So there was a finger or tongue of a glacier that sat here for a while and was dropping out its sediments, growing at the origin, and it's melting at the terminus. So that is a terminus. It's just dropping out a sediment that glaciers moved, and then it moved back and sat there for a while, dropped out sediment. All Cape Cod is 5 piles of sand, essentially, that got left there from a glacier. So before the last glacial maximum, this was not here. So Cape Cod is the product of erosion of the rest of New England. So deposition is when they stop transporting, moving them into their final resting place called a basin. The ocean is the last basin, the terminal basin in all products of weathering. But you can move them into a lake or deposit them in a river, deposit them in some low-lying area. So now, in this process of making sedimentary rocks, we have the sediment sitting there, but it's not a rock, right? If you went and scooped it up right after it had been deposited, it's still just sand or gravel or whatever it is. So the last 2 things that have to happen is you have to compact the rock. And the way that compaction occurs, you again have an intuitive feel for compaction, right? You squish it down. The way that compaction occurs is that the center of Earth's gravity is down here at the center of Earth, and you have pulling towards the center of Earth by gravity. And so you're compacting those rocks, and the notable thing here is that water is driven upwards. So remember that water for a minute, because the next slide will be cementation. But you're driving the water up, and you're compacting the sediment so the grains are closer together. There's not the air space or water space between the grains. They get close together. You see these depositional environments. We'll spend some time in each one of these during the course of this semester, whether it's a mountain for earthquakes and for landslides, and then coastal areas for river flooding will be here. So you're laying down these environments, beaches when we talk about hurricanes, and then offshore we have marine mud. Marine mud, if you scoop it up, if you were here and you took a scoop of it, it's about 80% water. So you can imagine that water is not a very good agent in making a rock. So you squeeze that out, you drive it upwards, and then you're compacting it. That's a way that you're going to make the sedimentary rock shale. So you squeeze out the water in the air, and the last step is that with this water, when the water is driven upwards by the process of compaction, the solutes, remember those products of chemical weathering, one atom sitting around in water, get left behind. They precipitate out of the water and they cement or seal the grains together. So that's the last process that's called cementation. And then as an aside, like we have this combined term erosion, which is weathering and transport, lithification, turning to stone, is a combined term that describes compaction and cementation. That's the last step in making sedimentary rocks. You're turning it into stone. So if there's a lot of sodium and chlorine that got weathered from the rocks chemically, and it's sitting in that water, and the water gets driven upwards, that will reprecipitate and glue the sediments together. Now you have a sedimentary rock. Igneous rocks, I'm not going to say very much about, for the reason that we're going to spend a whole day on them when we talk about volcanoes. So igneous rocks, for now, just know that they're cooled magma or lava, and as they were liquid that then turned into solid or a mineral, they're the starting material for all of Earth's rocks. Many different kinds of igneous rocks. They're beautiful. They're spectacular to look at. And again, we will look at these a lot later on. So for now, understand that we can distill these down to really sort of integrating them in with tectonics, which we'll learn about in a couple weeks, integrating them into our larger picture. We can think of 6 different rocks, and that's really all that you need. And really, you can think of two end members. So this is granite and rhyolite. These are made of the same things. That's when it cooled slowly underground. That's when it got shot through a volcano. Chemically the same, but looking at it, the crystals are larger in this one than this one. These are land rocks. And color is a very good diagnostic indicator of igneous rocks in a way that it's not with minerals. If you see light pink rocks, you know that they were formed on land. For those of you who are following along in the notes, I'm going to skip this middle one for a minute, go to this one. These are ocean rocks. These get shot through a volcano on the seafloor or cool slowly underneath the seafloor. They're dark in color. This is ocean, more like the composition of our mantle. Now I'll go up one. Diorite and andesite, these are the intermediate rocks. This is what happens when you mix the two together. These would be formed at coastal environments. So granite and rhyolite, land, gabbro and basalt, ocean, diorite, andesite, and intermediate when you mix them together. Again, we're going to go into great detail about these when we talk about volcanoes. So we'll end with metamorphic rocks. Metamorphic rocks are rocks that have been deformed. It comes from the Greek word change form. And they have been deformed or recrystallized. The important thing here is in the solid phase, solid state changing. It's amazing to me that you can make these changes that I'll show you and never have any melting occur. You're applying heat or pressure and you're changing one set of minerals into a completely different set of minerals without any melting going on. Oftentimes rocks that are metamorphic have these folds and faults in them, and we will look at this when we look at tectonics. The folding and faulting is important. So three things really make metamorphic rocks. Heat, anything that's in here that gets amalgamated will just change the chemical composition. This will ultimately be an igneous rock. But you see this zone of of heated rock here around the edges of a magma body, contact metamorphism it's called. You can cook rocks. So for example, taking limestone and turning it into marble. It's the same chemical composition, but it looks a lot different. So this happens near rocks, near the magma or mantle. Pressure is from the weight of the overlying rocks. So this would happen in tectonics when one plate is sliding up over the other one and pushing down. You're squeezing it and turning it into a different rock. And then the last thing that happens, and these usually happen together, is chemical fluids that are circulating around in the subsurface will carry ions from one place and deposit them elsewhere. So this is hot, usually in association with the heat. Fluids will move around and facilitate the grouping of different minerals. And the classic sequence that we like to look at, also a very simple set of rocks. The classic sequence is here. You have these slides. And what's happening is as you heat or squeeze these rocks more and more, you're turning them from clay to mica to feldspars and to amphibole. So here's just the pictures to end. There's slate. By squeezing and heating slate, you turn it into this intermediate called phyllite. Mica grains start to grow. So it's all clay. Clay smashes together and makes some mica grains. When you squeeze or heat it more, the mica grains get bigger and it turns into schist. So these are just the pictures of that diagram. And then any more heating or squeezing and you turn it into gneiss. You've taken micas and you turn them into